We're going to start our discussion of control volume laws with the idea of conservation of mass. Now, conservation laws allow us to describe almost everything in the universe. We can look at mass, momentum, and energy. We can use the second law, which is a topic for thermodynamics, to account for entropy. We're going to start with conservation of mass because it's one of the simpler versions of the control volume laws. We start with the Lagrangian viewpoint, the idea of a control mass. So for our control mass, we use psi equals 1. We're just interested in mass. And by definition, no flow can cross the boundary because it's a control mass, and mass can't be created or destroyed. So the Lagrangian derivative has to be 0. So this lets us simplify the equation a little bit. So now we can use Reynolds transport theorem and substitute, and we can find the conservation of mass for a control volume. This is the most fundamental definition of conservation of mass, and it's the equation I want you to start problems from in this class. You can then simplify it by using assumptions. For instance, you could eliminate the time derivative by assuming steady state, or you could remove velocity from the integral by assuming that velocity is uniform everywhere. We'll talk about that in a moment. I also want to note that this equation has wider applications than just mass in and mass out of a volume. The one group neutron diffusion equation is actually a modified version of the control mass equation. If you replace density with flux and you allow mass to be created or destroyed by nuclear interactions, you have this diffusion across the surface of the control mass. So what happens then is d phi dt is no longer 0. So you end up with this version of the equation for neutron diffusion. So we can revise it to change the equation a little bit and come up with a control volume formulation for the diffusion equation for neutrons, where you have change in phi is equal to flux in minus flux out plus production minus absorption. Here, flux in and flux out are described by the diffusion constant, and we were able to eliminate the velocity term because we don't have a flow. There's no flow for the neutrons. Now, we can simplify conservation of mass with many different methods, and you should try to remember the effects of the assumptions we're going to talk about here because we'll use them to solve problems. So, for example, if we have an incompressible fluid, we can remove density from our equations, from our integrals and derivatives at least, because density no longer changes. So this makes our equations much simpler to solve. If we have a fixed control volume, we know that the volume is a constant, so dv dt is going to be 0. We also know that the control volume velocity in the conservation of mass equation is going to be 0. We can assume uniform flow, which allows us to take the velocity out of the integral in addition to the density. So that helps us simplify problems. Finally, if we have a single inlet and outlet, we can actually reduce the equation to mass flow rate. The integral over the control surface just gives us the mass flow rate. Here it's important to note we have the velocity dotted with the area, and we use the v dot a equals va cosine theta here. So this actually explains the relationship between the directions and the sign, right? If theta is less than 90 degrees, the value of the cosine is positive. If it's greater, the value of cosine is negative. This is how we explain the sign convention for the dot product. If we have multiple inlets and outlets, we just sum over all of the inlets and outlets. So we get a total over the control surface is the sum of all the mass flow rates. So if we do that, we can actually reduce conversion or conservation of mass to 0 equals the sum of all the mass flow rates for a steady state uniform flow case. So this is a much simplified version of conservation of mass. In practice, always start from the fundamental equation on the previous slide and then apply assumptions until you reach a case that you can have that's simplified and you can use to solve your problems.